This is kind of a large proof, so bear with me as we work through it. The goal of this is to come up with more equations that describe simple harmonic motion. Right now, all we've got from applying conservation of energy is we know the max speed is root k over m multiplied by the amplitude. I'd like to get a whole group of equations so we can figure out more about this thing that happens to be vibrating. It's a very cool proof. We're going to start off looking at a two-dimensional circle and then talk about projection and equate it to simple harmonic motion. So here we go. Consider a mass m that's going in a circle with a radius of a and it's moving at speed v naught. I couldn't subscript, so this is supposed to be v with a little subscript. You'll see why I chose those particular letters as we work through it. If we were to consider this from the top view, we've got a circle. The radius of the circle is this letter A. The mass is at the end of it, so way out there. The mass is moving at some speed v naught. From centripetal motion, we know that the speed is always tangent to the circle, so at this split second, the v naught is pointed that way. If we were to just watch this thing for a bunch of time, it'd be kind of like the rubber stopper lab. Imagine watching the rubber stopper lab from the top. We would just see this thing tracking out two-dimensional circles over and over again. So just going around in a circle at a constant speed as long as we watched it. Nothing, we're going to use centripetal motion, but there's nothing simple harmonic motion about this yet. But what if we could use our imagination? If I can find a simulation on the computer, I'll share the link. But for now, we're going to use our imagination. What if instead of this object going in its two-dimensional circle, what would it look like if we sort of bent down and looked at it from the side or the front of it? What if you were doing the rubber stopper lab and we shone a really bright light on your rubber stopper as it went in circles and we looked at the shadow on the wall? That's what we call a one-dimensional projection. You'll learn about that a little bit in math class when you talk about vectors. So we're going to have to use our imagination. What if we looked at that 2D circle, but what if we sort of bent down or mounted a camera so we're looking at it straight on? What we would see is if this was kind of when the rubber stopper is at the center of its circle, it's going to go sideways till it gets to that far away point. That's going to be a distance that we happen to call A. Then it's going to turn, come back through its middle point, back to the other. Oops, if I could draw this nicely, those should be symmetrical. Let's try again. Come back this way till it gets to that other extreme distance and turn around and go back again. That's another distance A. As it whips through the center, that's when it's going its fastest. That's when it's going v naught. If we could watch this thing from the side, we would just see it wobbling back and forth over and over again. Really fast through the equilibrium, slow down and stop over here. Then really fast through the equilibrium, slow down and turn around. If we could watch this thing going back and forth, I don't know if it's simple harmonic motion, but it's definitely some sort of harmonic motion. It's wobbling or vibrating back and forth. It's got its maximum speed when it goes through the equilibrium, which kind of matches what we saw with simple harmonic motion. It stops for a split second at the end point. So it looks like simple harmonic motion. We'll have to do a little bit of force work to figure out if it actually is simple harmonic motion. Even if it's not simple harmonic motion, if we go back to the 2D version, so like the top view, we've got our amplitude of A. It's cruising tangentially at some speed v naught. It's a mass of m, whatever that is, the rubber stopper. If we were to just tackle it from circular motion, whenever anything goes in a circle, we say F net equals ma. In the rubber stopper lab, we called it tension because we knew it was a string making it pull it into the middle. I'm just going to leave it as F net for now. But because it's going in a circle, we know that the A turns into V squared over R. Because it's going in a circle, we know that V equals D over T. It's doing a full circumference every time period. We can go one step further we know that the radius is letter A. And over here, we could do the same thing. F net equals mv squared over A, since that's the value of the radius. We need a v squared, so if I take this one and square it, we get 4 pi squared A squared over t squared. Subbing that into F net, so taking a look at that, on the numerator I'm going to have an m and a 4 pi squared, so just the normal way we write is we pull the numbers to the front. 4 pi squared, we've got an m. We had an a squared on the numerator of the v squared, but we've got an a on the denominator, so the a's cancel out to make just a straight up a, and I can't do anything with the t squared on the denominator. So this messy thing connects the net force to some circular motion properties. We haven't really done any simple harmonic motion yet. We could have done that with any circular motion thing, but file that away. We're going to use that in a little bit. To make the jump to simple harmonic motion, we're going to assume, or we're going to suppose, instead of a string connecting the rubber stoppers that spins in a circle, when we did the lab, there was gravity on washers that was generating the tension. What if instead of that, what if instead of a string with washers, it was just a spring? What if we had a spring and we connected a mass to the end and we spun it in circles? We'll say that the radius of that circle is A. We'll say that's going at some speed v naught. If it's an ideal spring, what we're going to assume, it's hard to find one of these. I have one in class. I'll show you when you're in class. A spring that actually collapses to a length of 0 when there's no force on it. And the more force you put on it, the longer the spring gets. Just instead of a spring that had some length, it starts off that it's 0 long. And then as you pull it, it gets longer and longer. There are springs that are like that. They're different looking. Instead of a regular coil, the coils sort of nest inside each other. Remind me to either post a picture or I'll show you one when you get to class. But if we had a spring like that and attached a mass to the end, then we could say that F net is the force of the spring. The force of the spring is always K times S. This is the exact condition for simple harmonic motion. So if we go back a step and we say that this object that's going around in a circle is connected to a spring instead of a string, we already knew it looked like simple harmonic motion. When we switch to that projection, the force that's making it accelerate is a Hooke's law force. That means the force is proportional to the distance. That is the condition for simple harmonic motion. So we can say that this circular motion, if it's driven by a spring, that means that it is simple harmonic motion. If we consider it going around when it's at that farthest point, then we can say that the S is actually that special letter A. So our F net is really K times A. That's how much force the spring is putting on it. From what we were just yabbering about from centripetal motion, we also know that F net from the star is 4 pi squared ma over t squared. Take a minute to look at that one. It's weird how we came up with it, but if a mass on the end of a spring is going in a circle, we know it's simple harmonic motion because springs follow Hooke's law, and that looks like the simple harmonic motion condition. When we push centripetal motion, we get that 4 pi squared ma over t squared thing. That's equal to the spring force, which is K times distance. We gave distance the special letter A. If we clean that one up, the A's are going to cancel. I'm curious, what I'd like to get is t squared. If I flip things around, t squared is equal to 4 pi squared m over k. To clean it up a little bit more, if I want to get t all by itself, I need to take the square root of both sides. The square root of 4 is 2. The square root of pi squared is pi. The square root of m over k, well, I can't do anything with it. It stays the square root of m over k. This is a very cool general equation for the time period of something going through simple harmonic motion. The time period only depends on the property of the system, the K of the spring, and how heavy the mass is. Doesn't depend on amplitude. That'll tell you how many seconds it takes something to wobble back and forth. That's our, well, kind of our second, but that's an important simple harmonic motion equation. We're not done yet. We're going to try and get a couple more. If we go back to our projection, or sorry, our circle, it's at an amplitude, sorry, it's at a radius of r. At that split second, its velocity is tangent to the circle, so it's pointed that way. Oops, what happened? There we go. V naught's pointed that way. I'm curious about the 1D projection. So what would it look like if we just sort of added after the fact an x-axis? What would the shadow on the wall look like if we shone a light through it? Well, we'd have this object. I would only see it at sort of this range of positions, from outside the radius of the circle on the right through the equilibrium to the radius on the left. At some arbitrary time, we would be at some position x. If I call this angle theta, then I can go one step farther. At some arbitrary time, x is adjacent to that theta, so x is equal to a cosine of theta. I can do something similar with the velocity. This is a little bit messier. The projection of the velocity is pointing in the opposite direction. So it's really v naught's pointed tangent to the circle, but if I'm curious about what it's doing in the x-axis or its projection, that would be what I drew in purple, that v side. Takes a little bit of trig here, a little bit of geometry. We got a z pattern, so there's a theta in here. If that's a theta, then this angle in between the v and the v naught is 90 minus theta. If that's the case, then this angle up here is the same angle theta. So in my v triangle, my projection of the v is opposite the angle, so that's a sine relationship. And because of that opposite direction, after the fact, I need to put in a negative. Calculus people, when you get to derivatives, the derivative of position is always velocity. The derivative of cosine is negative sine. So the calculus would have had the negative done properly. For now, just trust me that I have to add the negative to fix up the direction. Okay, those are nice equations, but they're not great because they hinge on theta. I'd rather have them in terms of time. So I've got to do something brand new that we don't see right away in high school. I've got to define a new quantity. If something's going in a line, something's moving linearly, then we say its speed is distance over time. That tells you how many meters per second it goes through every second. In this case, though, our theta is related to how quickly it's going in a circle. So we could call this rotational or circular. We can track how fast something's going, not in terms of how many meters it's traveled, but in terms of what angle or how many radians it's traveled. So instead of meters per second, we'll use degrees or radians per second. And this speed is given, we call it rotational speed, it's given the Greek letter omega. So a new quantity is rotational speed, omega is theta over t. Or if we rearrange it, theta is equal to omega times delta t. We can sub that into those two equations we just came up with to get nicer versions. X is equal to a cos omega times delta t. So that's a function that tells us where a simple harmonic motion object is at any particular time. And the other function, v equals negative v naught sine, then in brackets, omega times delta t. That's a nice equation that tells us how fast it's moving at some arbitrary time. Now, as nice as those equations are, they only work if we really understand this omega thing. So let's go back to omega. Omega is theta over time. If we consider one full vibration, I know that one full vibration, sorry, but we got to use radians, is 2 radians, and it takes a time period to do that. So omega we can define as 2 pi over time period. So in these equations for omega, we could do a little bit of work to figure out the time period, and we could sub in 2 pi over time period to use those x and v equations. Or an alternate way is if you compare to what we came up with earlier, we said that time period was 2 pi times root m over k. If we flip-flop that around, I can get 2 pi over t is equal to, got to bring the t to the denominator, so I got to flip that other stuff to the other side. That's equal to root k over m. So another variation for omega, if we know the time period, omega is 2 pi over time period, or if we know the properties of the oscillator, the system, the k and the m, omega is also root k over m. I've typed a summary, but here are our new equations. Omega is a rotational speed. It's almost like a frequency number. It tells you, it communicates how quickly the object is vibrating. It's got two equations. It's related to the time period by 2 pi over t, and it's related to the properties of the system. It's also root k over m. From our crazy projection idea, our position follows a function related to the cosine. So the position is a cos omega times t. Speed follows a sine function. Speed is negative v max sine omega times t. Breaking down our circle and applying some centripetal motion, we got the time period equation. T is 2 pi root m over k. And to start it all off, without even using this crazy proof, we knew that the max speed from conservation of energy was root k over m. That derives all our crazy equations for simple harmonic motion. We'll practice it. That'll be the next couple of video clips. We'll practice using the equations. It'd be neat if you could follow the proof, but as always, I won't get you to memorize them. Just